Raise your hand if you know the Lightning Network. Okay, most people, okay, nearly everyone. That's awesome. Cool. So the very first talks are all going to be about the Lightning Network, mostly. You know, challenges in implementing the off-chain payment network, routing algorithms, privacy implications, potential attacks. Then afterwards, you know, we're going to think about, can we use SGX? Can that come to the rescue and help build these payment channels? Oh, my slides have disappeared. Awesome, okay. Can we build non-custodial exchanges using off-chain solutions? And actually, Zcash supports payments. So the Zcash one will be tomorrow. But actually, Zcash can also support payment channels, which is awesome. But actually, you know, payment channels, like they sort of emerged in 2013. They evolved a bit in 2014 and 2015. But actually, can we do a bit more? Can we do more than just payments in a channel? And this is sort of like the second half of the workshop. So actually, as I mentioned, there's like 6 or 7 splintered groups working on state channels. So actually, we have several different constructions on how to build state channels. And we're going to learn about all those tomorrow, and a little bit in the afternoon as well. Also, like when I think of a state channel, I normally think of a single application. You know, let's play poker off-chain. But actually, some of these constructions support multiple contracts off-chain. So we could do poker, we could do an auction, and do payments off-chain as well. So we'll learn about that. And actually, when you think about the definition of a state channel, what you think of is that there's 2 parties. You have a deposit into a channel, and then they can do the interaction. But what if 2 parties don't have a direct channel? What if Alice is connected to Bob, Bob is connected to Charlie, and Charlie is connected to Dave, and Alice and Dave want to play poker off-chain? We're going to learn that's also possible. So that's really cool. And finally, we're going to have some different topics as well. You know, can we do verifiable computing off the blockchain? You know, can we do this large computation and then do that within a state channel? Can we do off-chain casino and poker games? And we're going to learn that, but I guess that's the last session today, isn't it? But that's going to be really exciting because that's a live demo. And of course, are Bitcoin and Ethereum channels compatible? Now, what I'd also like to mention is while we were organizing and the lesson, the takeaway, what I really want to get out of this workshop is, are state channels useful? I mean, state channels have their caveats. Everyone always has to be online, otherwise you can get cheated. So are they useful or are they overkill? Let's find that out in the next 2 days. And also when I organized this, and our sponsors. We have 5 sponsors, which is awesome. So I'd like to say thank you very much for sponsoring our event. And finally, what I'd also like to highlight is that when we were organizing this event for the past 6 months, me and Alicia kept exchanging stickers. Every time there was a good event, a bad event, and you know, we were just like, what the hell just happened there? So this is sort of like our experience of organizing this event. It's the first one I've ever organized, so I'd really like to thank Alicia and the Binary District team for really pulling this event off. So can we just give them a round of applause? Thank you very much for helping me with this. And let's begin. Oh, and to the moon. You know, so yeah. Hopefully that'll be the theme of this event. So the first speaker up is Pedro. Okay, awesome. So Pedro's coming up now, and he's going to talk about privacy and routing on the Lightning Network. So come on up. There you
go. Okay, good morning, and thank you everybody for coming this early this morning on Saturday. I'm really glad that you're here. And as Patrick said, I'm going to try to talk a little about these multi-hops for secure, privacy-preserving, and interoperable payment channels. Yeah, this is me. I'm the speaker, yes. So because I'm the first speaker, I thought of giving a really 30-second introduction about what is payment channels, but most of you know, but just in case that somebody doesn't. So I guess that you agree that today with me that we have some scalability problems in Bitcoin, right? So we have a low transaction rate, we have to pay high fees for the transactions that we do in the blockchain. And we expect that the growth of the number of transactions in blockchain keep growing, actually in a fast pace. So the problem is going to become only worse and worse. So we need to do something about it. So, and as Patrick said, let's try to solve it, or at least to have a good idea of how to solve it in these 2 days. One approach that we have so far is these payment channels. And the way I see it, actually, I would like to see it is this gift card. So basically, I go to a shop, I put $5 in a gift card, And after that, I just use the gift card off-chain. I just use it in the shops to pay for things. And the only thing that happens is that there is a little number, a balance in the card that changes, but I don't have to interact with the shop anymore. And at the end, when I finish with the card, I go and I get whatever balance is left back in dollars, actually. So that's the same idea as with payment channel. So we first create a deposit transaction where Alice, in this case, puts a deposit, so with Bob. And of 5 Bitcoins, probably Alice is super rich because 5 Bitcoins is a lot, but just for the example. And after that, Alice and Bob can pay off-chain between each other. And at the end, when they are done with it, they can redeem back the balance that they have in the channel. And in the end of the talk, I'm going to try to use this figure for payment channel. One idea would be that each of us open a payment channel with everybody else in the world so that we can pay each other. But as you can imagine, this is not really realistic because you have to lock coins in each of the channels. So I can open a few channels with my friends, but I will not have enough money to pay to create a channel with everybody. So what happens in reality is that I open a few of them, and then I use other payment channels to pay other participants in the network. So for example, imagine that Alice wants to pay to the cat, but she doesn't have a channel with the cat. So Alice can use the payment channel with Bob to pay 1 Bitcoin, and Bob will relay this payment to the cat. As you can imagine, there are several security and privacy issues in such a system, and we're going to see some of them today. I wanted to mention that, as most of you know, and we're going to see most of them in these 2 days, there are current deployments and current proposal for payment channel networks. So in the Bitcoin, we have Lightning Network, Enlighten, SIG, probably some of them that I'm actually missing. Ethereum, we have the Reddit network. There are proposals also for Bolt. And as I said, you will hear many of them these 2 days, actually. That was the 30 seconds, probably 1 minute introduction for payment channels. I wanted to show also what my research group does about this. So as Patrick mentioned, there are many people doing research in this area. So in my group, we are trying to look at this from a formal model, from a formal part of view, and try to formalize security and privacy notions of these systems, and analyze the current system corresponding with these formal models. For example, recently we have a paper in which we show that in the current Lightning Network, it's impossible to have a strong anonymity, or strong security properties, and a strong concurrency at the same time. So this type of trade-offs is the one that we are interested on. And in this paper, what I'm going to show today is some cryptographic constructions that have some formal security and privacy guarantees. Okay? And that's what we call these MultiHop Locks. Probably if I tell you that we want to have secure off-chain payments, we all agree. But if I ask you what do we mean by security, probably we will have different opinions. So in order to agree, what we need is a security notion, it's a security definition. And intuitively, probably what we want is this balanced security, basically that honest users don't lose coins if they are part of a payment, if they're intermediate in a chain. A bit more graphical, so imagine that we have a payment from Alice to the cat, and there are several intermediaries. And some of them can be malicious, some of them can be honest, like Bob here. And the honest intermediaries have some balance in the channels. Let's say that they have 10 Bitcoins. What we want is that after a payment, the balance of Bob doesn't decrease. So it should never be the case that Bob participates in a payment, and after the payment, Bob has less coins than before. That should not be the case. Or in crypto terms, the probability that this happens should be really negligible, should be really small. So after we formalized this property, we looked at how the Lightning Network is actually trying to achieve that. And they use this HalfSign lock contract. And just a show of hands, how many of you know already about this HalfSign lock contract? Okay, probably everybody, so let's do it quick. So Bob chooses this hash function, and then chooses value x and calculate y, and give this value y to Alice. Now Alice can do this conditional payment such that Bob can only redeem it if he knows x, the preimage of the hash function, and he knows how to sign this transaction. Okay? So he knows how to sign because he has the secret key, and as soon as he learns x, he can redeem the money. And then the contract is finished. I'm sorry. And as you know, because you told me, the Lightning Network actually used this idea to chain payments one after the other in a payment path. So the cat will give the preimage to Alice, and Alice will do this HalfSign lock contract in each of the hops from the sender to the receiver. And at the end, when the cat receives the contract, she publishes the pre-image, and then the payment channels are actually settled. Probably one thing that you are less familiar with is with the concept of privacy in a Lightning Network, actually. And again, probably we all agree that we want privacy, but we probably will not agree on what is the definition of privacy itself. So for us, privacy is defined in the terms of relationship anonymity, and intuitively means that we want to hide from the intermediaries who is paying to whom, which we believe is an interesting property. And a bit more formally, we define it as follows. So imagine that we have 2 senders and 2 receivers, 2 Alice and 2 cats, and they use the same path. And again, some of the intermediaries can be malicious. Imagine, for the sake of the example, that the blue Alice is paying to the blue cat and the green Alice is paying to the green cat. What we want is that the intermediaries, the malicious guy, cannot really tell who is paying to whom. Okay? So in terms of probabilities, the probability that the attacker actually correctly guesses that the blue Alice is paying to the blue cat is close enough or negligibly close to the fact that the intermediary or the malicious guy is wrong. So the malicious guy thinks that the blue Alice is paying to the green cat. So if these probabilities are really close to each other, that means actually that the malicious intermediary doesn't have information, doesn't learn who is paying to whom. And the interesting point here is that when I started to study this in the Lightning Network, I thought that, okay, everything is off-chain, so don't we have privacy actually already? Because nothing is going, or not much information is going to the chain. Don't we have privacy already? And the question is actually no, and we will see why. So the idea is that now when Alice is paying to the cat, they will use this HalfSign lock contract in the different payment channels to perform the payment. And the fact that, and the current way, the way that currently Lightning Network works, they will use the same condition Y for the whole payment, okay? The same happens when the green Alice pays to the green cat. They will choose another condition, Y prime, but they're using the same condition over the whole path, okay? So now the adversary can see, okay, I have a condition Y from blue Alice, and I also relaying this condition Y to the blue cat. So he can really see that the blue Alice is paying to the blue cat, just by looking at the condition itself, okay? So the actual problem that we have is that the same condition value, the same lock actually is being used for all the hops in the payment. And this is one thing that we are trying to solve in our group. But before that, I wanted to show you, this is what we think is the current state of the Lightning Network, or payment channel network, which are deployed in practice. So we saw that they have some security, but they lack some notion of privacy. And we are also interested in looking at interoperability, so how well they interoperate with other payment channel networks. For example, now the Lightning Network requires this hash function, and either other payment channel network have it and they can talk to each other, or they cannot interoperate, they cannot talk to each other yet. And also the transaction size is not the optimal size, in the sense that now the transaction for a payment channel requires the signatures plus the script for the HalfSign lock contract, okay? And so we will see we can do better than that in terms of size. So let's try to fix these privacy issues first. For that, what we thought is, why do we need actually HalfSign lock contracts, or why we need this hash function in the first place? Can we do something else, and do we get some advantage out of it? Okay. For that, what we thought is, okay, let's use one-way homomorphic functions instead of hash functions and see what we get out of them. So one-way functions have mainly 2 properties. One is this one-wayness, which is pretty much as the same as hash functions. Given the y, which is the f of x, given the output of the function, you should not be able to figure out the input of the function. Okay? So given f of x, you should not be able to figure out the value x. And the other one is this homomorphic property, which means that if I give f of x and f of x prime, you can put it together, and what you get actually is the function of the 2 inputs, x and x prime, at the same time. And we saw that this is enough actually to have these locks, the MultiHop locks, the same functionality as the HalfSign lock contract. And we're going to see how one do that. So imagine the same setting, Alice wants to pay to cat through Bob. So Alice is going to create 2 values, x0 and y0. Okay? Y0 is just basically the function x0 times g. And x1 and y1 is constructed as depicted there. So y1 is the putting together the f of x0 and f of x1. So put x0g concatenated with x1g, and this is the conditional y1, okay? So intuitively means that in order to reveal the preimage of y0, one should know x0, and in order to reveal the preimage of y1, one should know not only x0, but also x1, and the combination of them, okay? So what Alice does then is gives Bob these two logs, saying, look, there are two logs which are related by a value x1. I don't tell you the preimages, but you know that they are related by this value x1. So he's happy with that for the moment. And for the cat, gives the whole thing. So it gives the condition, y1, and the whole preimage, the x0 plus x1. So as soon as cat gets y1, she knows how to reveal the preimage. So she knows how to receive the payment. So like that, we actually simulate the two things that we need. So the receiver gets a contract that as soon as she receives the conditional payment, knows how to open. And the intermediary gets some condition that knows the relation between what comes in and what goes out, but doesn't know how to open in the first place. Okay? These are the two main operations that we need for multi-hops. Once the multi-hop is set up, then we can lock actually the payments. We can lock the coins through the path. So the first thing that Alice does is do this we call it OneWay has one-way homomorphic contract, which tells Alice, look, Bob, as soon as you give me the preimage of y0, I give you one coin. I give you one coin. But Bob, as we saw, doesn't know actually the preimage of y0 yet, so he's okay with that. And he forwards this y1 to the cat. As we saw, he's okay with that because he knows that these two conditions are related by x0 concatenated with x1. So he knows that as soon as cat reveals y1, he will be able actually to open y0. And we're going to see how that happens now. And the main important thing here regarding privacy is that these two values actually are now not correlated. So they are totally two different y values. And somebody being part of the payment, being part in some intermediary, cannot relate that two cryptographic logs belong to the same payment. Here I have shown only for two hops, but as you can imagine, you can do this with multiple hops, with more hops in a payment. Once the multi-hop has been set, then we can release them starting from the receiver, exactly as we do in the Lightning Network. So as we saw, the cat actually has enough information, so it can just reveal x0 plus x1, which is the preimage of y1. And then Bob gets this information, takes out the x1 part, and then gets the x0 and takes it as the preimage of y0. And he can do that again because he knew that these two were related in this manner. He knew that his value x0 was related with x0 plus x1 by this value x1. So he knew how to remove x1 out of it. I know it's a lot of crypto, a lot of details here, but I wanted to show you at least the intuition of how it works. Just I think what you need to take from this explanation is the following, is that it is possible to have a little better privacy in the sense that now it's not true that we need that all hops have exactly the same condition, the same y value. We can have something better than that. And I put it yellow because what we do in this project is trying to raise the bar of privacy a little, so the y values are different in each of the logs, but there is still other information that is public. So for example, the value that is sent in each of the logs, and also the time for each of the time logs. Right? So this project raised the bar a little, and one question that is open for us and we don't know how to solve is that if we have more than one hop, have let's say 2 or more hops in a payment, it seems hard actually to hide those values, to hide the payment value and the time blocks. We don't know how to do that yet. Another interesting point of this approach is this interoperability. So what we show here is that you don't need to use only hash functions. You can use any function that is in the family of one-way homomorphic functions, and you still have the lock mechanism. You still can build Lightning Network-like payments. Okay? So if blockchain 1 uses one-way homomorphic function 1, and another blockchain uses another homomorphic one-way functions, you can perform atomic swap. You can perform payments that part of it is in blockchain 1 and part of them is in blockchain 2, and everything will be fine in terms of security and privacy. And the other thing that we didn't solve here yet is this transaction size. So even with this approach, we still need the signatures for each of the hops, plus this contract, the one-way homomorphic contract. So we need these two parts in the transaction, okay? And so let's see how we solve this last part, how we do the transaction a bit smaller. And for that, we thought, okay, why do we need the scripts in the first place only for the cryptographic functions? Why do we need the scripts to encode these image and pre-image operations? And it turns out that actually you don't need them, and there is this concept of scriptless scripts. And the original idea was proposed by Andrew Poelstra, working for Blockstream now. And the main idea is that you want, or you can actually encode this condition, in the sense, this condition of image and pre-image, inside the Schnorr signatures itself. Okay? So if you remember, we have the signatures part plus the script, only for the condition. So we can take this condition and encode it in the signature itself. So we remove the part of the script in the transaction. In our work, we show in the paper, actually, we show how to do that formally, the formal description and all the algorithms, and also the analysis of how this ensures security and privacy notions. Here, just for you to have an idea of how this works, that Bob can think of some random value x and give it to Alice. And now Alice can give Bob what I call a HalfSign transaction, which means that Alice gives the signature, but this signature is masked by this value x. You can think of encrypted with the value x, basically just a modified version of the signature of Alice, such that when Bob knows this value x, can remove it from the signature and get the signature from Alice. And the other part that he needs is his own signature, but he can always create that because he has the signing key for that. And in that manner, we have actually encoded the cryptographic condition inside the signature itself, and we don't need anything in the script for the condition. And there are some interesting aspects with this construction. So the scripts are no longer required for the condition. So you can imagine we can extend this for multi-hops. We can use the same trick as before with x0, x1, and concatenated them to have more than one hop. And if there are also advantages, if you take these two signatures in Schnorr, actually you can put them together. So you can aggregate them, such that in the chain, in the blockchain, you have to put only one signature, but the verifier can verify that it's actually the combination of two signatures, one from Alice and one from Bob. And this has interesting properties in terms of what they call fungibility, in the sense that if we do that, a payment from a payment channel looks exactly the same as any other payment in the network, any other payment in which I alone pay to somebody. It has only one signature, the sender and the receiver. Here will be the same. It has the sender, which is the deposit, only one signature, and then the receiver. And this obviously improves this aspect that we wanted to improve, the reduced transaction size, in the sense that we don't use the script for the conditions. In terms of interoperability, it's still fine. It requires Schnorr signatures, which are available in some of the blockchains, but unfortunately are not available yet in main blockchains like Bitcoin or Zcash or Ethereum. So we will have to wait a little actually to have this approach actually deployed. So the last thing that we thought in this work is that what if instead of waiting, we try to do something like that, like this trick that we saw, but with ECDSA itself. Okay, what if we can do the same, but with this signature scheme, which is in Bitcoin today? And the question is that the point is that it's not really an easy problem, and was unknown actually up to the point that we tried to do it. And what we wanted to do exactly is the same. So to encode this cryptographic condition inside the ECDSA signature itself. But it's not easy, actually. So the main challenge is that the Schnorr signature has a really nice linear structure, which there is randomness plus the key times the message. And if you see the ECDSA signature has a really weird structure in the sense that we require inverse of numbers, this r minus 1. We need to get the coordinate of a value of a point r. And we also need the multiplicate shares of the keys. That means that instead of having key 1 and nicely sum it with the k2, we need to multiply them, and that in cryptographic protocols make the cryptographic protocol way more complicated. But at the end, we managed to get around these problems, actually, and we have a construction for scriptless scripts using ECDSA, so that we can use them today. And if you're interested in the paper, we have all the details for this protocol. And as a summary for this part, yeah, we managed actually to have the same nice properties for the reduced transaction size. Now, is interoperable is a bit better in the sense that now we can actually use it in the main blockchains today. So we can use it in Bitcoin or Ethereum today. And we still respect the security and privacy properties that we wanted to achieve. Just in the last 30 seconds that I have in the talk, I wanted to show that even this ECDSA protocol is a bit more involved than the Schnorr-based protocol. From the communication overhead and computation overhead point of view, it's actually it's really efficient. It's almost as efficient as the Schnorr one, and we require only about 500 bytes of communication and a few milliseconds for computation overhead. And currently, actually, this approach is being implemented for the Lightning Network, so hopefully it's going to be published soon, an implementation of these ECDSA-based locks. And the interesting property, I think even more interesting, is that it is possible to combine these three approaches that I told you today. So it's possible to have a payment channel with several hops, which one hop uses these one-way homomorphic functions, the next one uses Schnorr, and the next one uses ECDSA, and still the payment can go through, actually, along the whole path. Okay? And this payment respects the security and privacy properties. That's one of the main results that we found, and we found it interesting. And we are really looking forward to hear from you, actually, applications for these new lock contracts. We thought of atomic swaps and payments, but I'm pretty sure that there are many applications that we didn't think of yet. So the main takeaway from this talk, and I will be more than happy to answer questions now and talk to you later, is that there are payment channel networks that provide a scalability solution to current blockchains. But however, we have many open questions that we don't know how to solve yet. And in this work, we try to give answers to some of them. We provide a formal analysis for security and privacy properties for the different payment channel networks. We have designed different cryptographic construction for this lock part. And we believe that there are many possibilities of using these new cryptographic techniques for different applications. And I will be more than happy to hear from you these applications. And with that, I would like to thank for your attention. I will like to answer your questions. Thank you very much.
Awesome. Okay, that is working. Awesome. Thank you for that. We have time for one or two questions. So.
Just a question about the threat model in your work. So what do you assume the adversary can do? For example, what can the adversary observe? And also another question is, do you really consider Alice or Cat as the adversary?
That's a really good question. So what we assume is that the adversary is an intermediary in the path, and he can observe everything that goes through him. Okay, so payment channel networks are decentralized setting, and when you use a malicious node as your hop, you just basically give all the information. That's what we assume. And we believe that having the Alice, also the sender, the receiver, as a malicious guy is a bit not too unpractical. In practice, I kind of trust Amazon when I pay to him. But it will be interesting actually to look at that and see what it's on. And in the paper, we have more details of what happens actually when they are malicious. Mm-hmm.
Awesome. And any other questions or over there?
Let me just give you a microphone.
There was Bob generating some randomness,
Yes.
and I wonder what happens. And I didn't quite understand all of it, but what happens if the randomness has structure actually?
Yeah, that's a really good question. So I put it here only in Bob just because I didn't want to show the whole protocol because it takes a lot of steps. In reality, it's not Bob the one that creates the randomness, but Alice itself. So Alice creates, and that's the setup the same way that I showed for the one-way homomorphic function. So Alice creates the randomness, give a hidden way of the randomness to Bob, such that only when Bob gets the HalfSign transaction, can get that information plus the hidden randomness, combine them, and then get the payments. Yeah, that's a good. Yeah, like I didn't want to show all the construction because I thought it was a bit too much. Yeah, but good point.
Okay, awesome, Frank. Oh, one more question.
You didn't mention anything about timing considerations. I was wondering if you wanted to say something about the impact on timing of this approach.
Yeah, that's as I said, like in this work, we basically there are three aspects in a multi-hop payment. It's the value, the timing, and the cryptographic condition. And we think that we should take one thing at a time and try to look at it. So we look at this cryptographic condition and make it more secure and private. As I said, we are looking at the question, what do we do with these two others in a multi-hop payment? And I don't know if it's impossible yet, but we find it really difficult actually to hide these two values in a decentralized setting. On a multi-hop payment, where you have more than one hop. That's our idea now.
Just to expand on that a little bit, specifically about timing, I was thinking like there's this whole capital cost trade-off with linear growth in the number of links versus having a global timeout. So like this is the sprites thing. And I was wondering if you had any thoughts about the relationship of this approach to global versus linear timeouts.
I see. That's another good point. So here in this work, we are focusing on the Bitcoin-like capabilities that we have. So the approach that you're saying is more related with state channels, so you need more capabilities and more functionality in the blockchain below to do it. In the next project, actually, we are trying to look at that as well and see what extra functionality from Ethereum or from stake channels we can use and what extra properties we can get. So, yeah.
Awesome. Thank you for that. Can we have another round of applause for Pedro? Awesome.